In this example, we are asked to calculate the bond order and magnetic properties for the molecular ions C2+ and C2-. The strategy here will be to count the number of valence electrons in a molecule, select the appropriate MO diagram, and fill in the electrons in the MO diagram using the Aufbau principle, Hund's rule of maximum multiplicity, and the Pauli exclusion principle. So since we're dealing with C2+, we should recognize that we have to use the MO diagram on the left, where the 1 pi U bonding MO is lower in energy than the 3 sigma G bonding MO. So for C2+, we can imagine that one of the atoms in the molecule consists of carbon, which has the valence electron configuration 2s2, 2p2, and so we would have 2 electrons in the 2s atomic orbital and 2 electrons in the 2p atomic orbital. And the other atom we could imagine as consisting of C+, which has the valence electron configuration 2s2, 2p1, giving us 2 electrons in the 2s atomic orbital and 1 electron in the 2p atomic orbital. So this gives us a total of 4 plus 3 equals 7 valence electrons to distribute in our molecule. And we would have to distribute those in our molecular orbitals, which are located in the middle of our MO diagram. So starting with the lowest energy molecular orbital, we would place 2 electrons in the 2 sigma G bonding MO, 3, 4, so another 2 electrons in the 2 sigma U star antibonding MO, 5, 6, 7 electrons in the 1 pi U bonding molecular orbital. So this would give us an MO diagram as shown here, and we could write therefore the valence electron configuration of C2+ as 2 sigma G2, 2 electrons in the 2 sigma G bonding MO, 2 sigma U2, 2 electrons in the 2 sigma U antibonding molecular orbital, and 1 pi U3, 3 electrons in the 1 pi U bonding molecular orbital. And so from the MO diagram, we can clearly see that C2+ is paramagnetic, since we have 1 unpaired electron, as shown here. Next, we can calculate the bond order for this molecule, and as we recall, the bond order is calculated using the equation 1/2 times the number of electrons in bonding MOs minus the number of electrons in antibonding MOs. And so we would have a bond order of 1/2 times 5, 2, 4, 5 electrons in bonding MOs minus 2 electrons in antibonding molecular orbitals. So this would give us a bond order of 3/2, and therefore this molecule is stable since the bond order is greater than 0. Next, we'll look at the MO diagram for C2-. Now, since this is also based on carbon, it uses the same diagram as the one for C2+, namely where the 1 pi U bonding MO is lower in energy than the 3 sigma G bonding MO. So for C2-, we can imagine that one of the carbons is present as carbon, which has a valence electron configuration of 2s2, 2p2, indicating that we have 2 electrons in the 2s atomic orbital and 2 electrons in the 2p atomic orbitals. Now, for the adjacent carbon atom, we can imagine that that might be present as C-, which has a valence electron configuration of 2s2, 2p3, where we have 2 electrons in the 2s atomic orbital on the other atom, and 2, 3 electrons in the 2p atomic orbitals on the other atom. So in total, this gives us 4 plus 5 equals a total of 9 electrons to distribute in C2-. And those electrons would have to be distributed in the molecular orbitals as shown in the middle of the MO diagram. So starting with the lowest energy molecular orbital, we would place 2 electrons in the 2 sigma G bonding MO, followed by 3, 4 electrons in the 2 sigma U star anti-bonding MO, followed by 5, 6, 7, and our 8th electron is in the 1 pi U bonding MO, and finally the last electron is placed in the 3 sigma G bonding MO. And this completes the MO diagram for C2-. From the MO diagram, we can see that the electron configuration can be written as 2 sigma G2, 2 electrons in the 2 sigma G bonding MO, 2 sigma U2, 2 electrons in the 2 sigma U star antibonding MO, 1 pi U4, 4 electrons in the 1 pi U bonding MO, and finally 3 sigma G1, 1 electron in the 3 sigma G bonding MO. And so this is the electron configuration for the valence electrons for C2-. Now from the MO diagram, we can see that C2- is paramagnetic, since we have one unpaired electron. And lastly, we can also calculate the bond order for C2-, recalling that the bond order is defined as 1/2 times the number of electrons in bonding MOs minus the number of electrons in antibonding MOs. So for C2-, we would have the bond order equals 1/2 times 7, where we have 2, 4, 6, 7 electrons in bonding molecular orbitals, minus 2, because we have 2 electrons in antibonding MOs, which gives us a total of a bond order of 5/2. And this is the information that we can obtain from the MO diagram for C2-.